Morning, everybody. Welcome back. I have to admit, I really didn't want to come back. I was in the closest thing to paradise that you could find in California. But I thought of you. And it made it all worth it. I was up in the mountains all week, and there was hardly anybody around me. It was so nice. Yeah, I got up there and saw the last snowfall of the season, and by the end of the week it was like 70 degrees. 65, 70, yeah. Pretty nice. Had a successful 50th wedding anniversary for my in-laws. Always good. So, yeah, fun was had by all. And then there was relativity. So I'll have you know that I did relativity over the break, but only because my brother-in-law was asking questions about it. Is it something in my look? Is there a sign that floats above my head that's like, ask me any dumb physics question you've seen on the internet?
It's just there. You can't see it though.
Yeah, we had a good talk. I straightened him out. But we've got a kit. I think did anybody think about it? No. Too esoteric, too weird. There's this part of you and me where we just like, this is science fiction. This can't be real. Hopefully today I will begin to show you the way. Depends on how far we get. Depends on how much of spring break inertia I need to work against, right? But let's just sort of begin a little bit with a review or a reminder of things that we did learn last time, or at least some key things. Let's start easy. Gamma. When we're doing relativity, we can calculate the gamma factor, right? And gamma is a straight up calculation. Do you remember what it was? 1 minus b squared over c squared, right? So like, in relativity, okay, you might feel like guessing about all the physics. It feels like guessing. Gamma is something you can straight up calculate, right? So in our problem up here, where we're given this relative speed, that's the speed that goes into gamma, right? Two different observers. A picture sometimes helps. In this particular problem, right, we are given that there is the Earth, and there's probably somebody sitting on the surface of Earth. It worked fine all last period for Physics 4a, and now it doesn't want to work at all. Give me a second. I have to, can't remember what I have to do. I have to do that. I need to do that. I need to restart it. And then start this again. And now, woo! Here. I don't know why it does that. Undoubtedly, there was an update of some kind. Okay, person on Earth, person on Carrot. It's a rocket ship. So we got astronaut, we got the Earth-based observers. They're measuring something. We'll get to all of that in a second. But if the Earth says that they're going 0.65 C, right? Say that way. Is there another way we could draw the problem? Yeah. Whose point of view is in this problem right now? That's the Earth, right? So if we drew it from the point of view of the astronaut, what would that look like? We would have astronaut, right? and then we would have Earth, and Earth would be going that direction at 0.65 c, right? So this is the science of relativity. There is no one frame of reference that is the correct one. There's different observers agreeing on relative velocity. And what's the other thing they always agree on, according to Einstein? Speed of light is the same. And it's that insistence on keeping the speed of light the same for all observers, regardless of their relative motion, that causes changes in time and how it's measured. So what we've got is a gamma factor 1 over the square root of 1 minus 0.65 squared. What happened to all the c's? Yeah, they all cancel out, right? That's why we write it the way we do. 1.316 is what I got. Gamma has no units, just a number. And when it comes to time dilation, it's involved in the time dilation equation. 2 times in time dilation equation, a dilated time, delta t, and a proper time, delta t sub t. And there's a definition of proper time that will keep you safe, and then there's all other ways of thinking about proper time which will lead you astray. You remember the safe definition, the thing that you have to check or look for? Same place. What has to happen in the same place? The events that mark the beginning and ending of a time measurement. So whatever things are going on that cause a person to start or stop a stopwatch, those events need to be taking place at the same location. That's how you know when a time is proper. So, we have been given a time in this problem by inference. What's the time measurement that's taking place? What is it? 1 minute, right? It's 55 beats per minute. So the time measurement is 1 minute. And the question, it's always the question that you need to sort of ask yourself, right? Is this a dilated time or is this a proper time? And to answer that question, you need to think about who's making the measurement and the events that they are using to make that measurement. So, what do we know about the 55 beats per minute? Who observes it? Who measures it? The person on the earth. And what events are going to take place for them to measure that 1 minute time interval? There's several different ways to think about this. Not all of them are wrong. To time 1 minute, what are they going to have to do? Start and stop a stopwatch. Do not fall into the trap of thinking about where the stopwatch is. Stopwatch is being held in the hand of the person on earth, right? But what events are they using to start and stop their stopwatch? What are they looking at? A heartbeat. 55 of them, right? Okay? So they start their stopwatch and start counting heartbeats. And they stop counting heartbeats, either maybe 1 minute shows on their watch, but more particularly after 55 beats goes by. The event was, astronaut was here, heart beated 55 times, and now astronaut is over there. The events, same or different places? Different places. Now, again, ways to get this wrong would be, well, Mr. Balogh, they're holding their stopwatch, right? And they start and stop their stopwatch at the same place. Then they're not measuring heartbeats, right? They're just looking at their stopwatch starting and stopping, right? Okay? You have to think about the events. This time interval of 1 minute is based on seeing an astronaut over there, letting a minute go by, and then the astronaut's over there. All the while counting the number of heartbeats that takes place. So the Earth-based observer, the person doing the measurement that does 55 beats per minute, okay, is measuring what kind of time? Dilated or proper? It's a dilated time. The events are happening in two different locations. So, we're going to take that dilated time of 1 minute, and we're going to find the proper time that the astronaut would measure. Now, let's see conceptually if we can make this jive with the definition of proper time. What does proper time mean? Events that are used to measure happen in the same place. As far as the astronaut is concerned, would they measure proper time for their own heart rate? I certainly hope so. Because the only way to measure dilated time of your own heart rate is for your heart to be beating in different places. It's not okay. Right? So, since the heart is in the astronaut's chest, right, and it's not moving relative to the astronaut, and the astronaut times 1 minute, and those beats go by, and they always happen at exactly the same place, the astronaut should be measuring proper time. So let's find out what the proper time would be for those 55 beats. Now, this is going to get a little bit interesting, but let's just see what happens. We're solving for proper time, so that means it's going to be the dilated time divided by gamma. So 1 minute divided by 1.316, which gives me 0.76 minutes. What physiological thing has to be the same? There's different times being measured here.
The beats.
The number of beats of the heart. There's a lub-dub that both of these people are all going to see. Those events, lub and dub, 55 times over and over again. Okay? That's the same. So for the astronaut measuring 55 beats, but instead not seeing it in 1 minute, but seeing it in 0.76 minutes, means that their resting heart rate is 72 beats per minute. Or in other words, this astronaut either needs to be less excited or needs to do more cardio. Right? Because the normal resting heart rate should be what? 60? 65? This is America, so 85? All right. We answered part A by doing part B first. I always prefer to do that with relativity problems, right? Because I can conceptually convince myself of either way. But the math usually helps me out. So she measures 72. Oh, did you see that they announced the Artemis 2 astronauts? Mm-hmm. There's astronauts that will be going around the moon next year. Can't wait. Starship might be launching next week. SpaceX's big rocket, the largest rocket ever made, makes the Saturn V look like a firecracker. Maybe next week. This week they're doing the wet dress rehearsal. Next week might be the flight. Stay tuned. This gamma factor is kind of interesting. Okay, we dove into the time measurement because I wanted you to have more practice in thinking about time and time intervals and events and things like that. But the gamma factor affects everything. Biological processes, time, as you're about to see, lengths. So you could have just taken the 55 beats per minute and multiplied by gamma and gotten 72. So kind of whichever way you want to work it, okay? A moving astronaut's heart rate will appear slower. The time interval between ticks and talks. It was Ratch's car. Who was riding on the front? Abel was riding on the front. And it was it Juan who was holding the right? Okay. Remember, Juan sees Abel's clock have to go that longer distance. And so a moving clock appears to run slow. A moving heart rate appears to beat slowly. And in fact, does. That's where it goes from just being sort of a philosophical construct of Albert Einstein's brain into becoming physics, where we can actually measure the slower growth rates of plants and people and things. Time moves slower for objects that are, from our point of view, moving. What I would like you to do right now is in little groups, get together, okay? And I want you to talk about proper time, dilated time, what's being measured. You have a 1 minute time interval again, right? So I want you to determine if that 1 minute is proper or dilated. Go.
Their point of view but their point of view,
I think the proper time is
All right. We have 1 minute. And which one is it? Is the 1 minute proper this time, or is it dilated still? On your exam, you have a 50-50 chance. Right? Pretty good odds in physics. Right.
the 1 minute is proper, we're trying to find the
Okay, who's doing the measuring?
astronaut.
Okay, the astronaut is doing the measuring, right? Well, so we have two measurements going on, right? We have the 60 beats per minute that is measured by who? People on Earth, right? Okay. And then we want to figure out what the astronaut measures. So, the safe definition of proper time, which is the more complicated one, but it is safe. Who, between the Earth and the astronaut, are the only people that can measure a heart rate at exactly the same location for the entire duration of the measurement? The people on Earth. Why? Because the lab person isn't moving relative to the lab, right? Whereas the astronaut, what is the astronaut going to see? I've already deleted it. Very clever, right? The astronaut, right, is going to see the Earth moving away. So as the astronaut tries to measure a lab person's heartbeat, no choice but to see those heartbeats happen in different locations. So the 60 beats per minute has been measured, okay? This 1 minute is very definitely a proper time. So to find out what the astronaut measures, take our gamma factor, 1.316, and we multiply it by our 1 minute, and we get 1.316 minutes, right? What's the thing that has to be the same? Number of beats. 45.6 beats per minute. So that is a very healthy lab technician. Probably running ultra marathons or something. Okay. Practice a lot. Trying to decide proper time and dilated time. Is the math here hard? You can do these problems really fast. You can probably do your homework pretty quick by guessing one, trying it. If it's not a green box, flip it and get a green box. You will fail your exam if you do it that way. You've got to find out why you got it wrong. I really advise you, try the homework, do your darndest. When you get it wrong, figure out where your thought process went wrong. Don't just accept, oh, I got it wrong, green box, move on. Because it's in that struggle that you're going to start making the corrections. Go to the end of the chapter, pull out problems. Again, the math goes really fast. It's the thinking about what's being measured, right? It takes a long time where you're going to have to do all the heavy lifting here. So you can try lots of problems this chapter because the math, and you just take the odd questions at the end of the chapter, the answers are right there, right? And see if you get their answer.
For this one, so the dilated time is the
1.316. Proper time is 1 minute, right? 60 beats per minute.
Oh, okay.
Right. If you think that time dilation is hard to wrap your brain around, we need to talk about the simultaneity of events. So, what does the word simultaneous mean? Happens at the same time. If you insist, Albert Einstein insists, that the speed of light is the same for all observers, they have to give up on time being the same for everybody, as well as length, as well as the order in which events take place. This is where it's going to go from philosophy to physics, because experiments will be done. You got to hold on. There's still thought experiments, but remember, physics is about being able to experiment, right? To prove or show or take the measurement that corroborates the model that underpins it. I'm gonna play this video twice. The first time, I'm just going to let it play all the way through without pausing it or doing anything, and let the tidal wave of information just flow over you and crush you. We will then go back, and I will stop the video at key points to talk about what's going on.
Consider two observers in relative motion. In this case, Albert and Henry, just for the sake of argument. At the exact place and time they pass each other, they observe a flash of light. A sphere of light expands outward from that point. Since each measures the speed of light relative to himself, each believes correctly that he is always at the center of that expanding sphere, even though they themselves move farther and farther apart. How can two people in different places both be at the center of the same sphere? To confirm his perception, each sets up light detectors an equal distance apart. However, while Albert's detectors register the light arriving simultaneously, he believes the light strikes Henry's detectors at two different times. Meanwhile, Henry sees the same thing in reverse. They agree on the speed of light, but they disagree on whether events happen simultaneously or at different times. This is not semantics, nor a petty debate. It means that time, as well as distance, has to be affected by motion.
How you doing? Make it stop, Mr. Man. All right, here we go.
Consider two observers in relative motion. In this case, Albert and Henry, just for the sake of argument.
Okay. Two observers moving relative to each other, right? They will see each other moving at the other speed, right? So half a speed of light, 0.9 speed of light, 2 miles an hour, doesn't matter what the number is. They both see the other one moving at that same, that's what relative speed means. Okay. And it's Albert and Henry because Albert Einstein and Henry Lorentz, Heinrich Lorentz, who was the mathematician behind relativity. They're arguing over something, okay? And under special relativity, what's the one thing that, well, two things that they agree on. One of them's relative speed. What's the other? That the speed of light is exactly the same.
At the exact place and time they pass each other, they observe a flash of light.
Okay. The flash of light happens where? At an exact point. What point is that? Right when they basically overlap each other, right? They're showing it spread apart, but really they've just passed over each other, right? So like the flash of light happens at the origin of coordinates, the center of their universes. And there's only that one time when those centers overlap, right?
A sphere of light expands outward from that point.
Why is a sphere of light expanding outward from that point? Light is a wave. It's a flash of light that happens at that origin, right? And the light goes out in all directions, forming this sphere, this bubble, right, of light.
Since each measures the speed of light relative to himself, each believes correctly that he is always at the center of that expanding sphere.
Did you catch the word? Correctly. They are both correct. They are both at the center of the same sphere of light, even though they're getting further apart from each other.
Even though they themselves move farther and farther apart.
I just said that.
How can two people in different places both be at the center of the same sphere?
Key question, right? Stop! Your brain is doing it right now. I can see it in your eyes. Okay? It's thinking about TikTok or something else because that's easier. Okay? Your brain wants to escape because I'm asking you to hold a dissonance in your brain about how people can be at the center of the same expanding sphere and yet be in different places at the same time.
Everything else is relative.
But that's an excuse.
Yeah, but
Okay?
you can go
So the question is, how can that be true? What are Albert and Henry about to do that makes this not philosophy, but physics? They are going to do an experiment. And what is that experiment going to be based on? Speed of light, the one thing they can agree on.
To confirm this perception, each sets up light detectors at equal distance apart. However, detectors register the light arriving simultaneously.
Why would Albert's arrive simultaneously? He's standing straight in the middle between two detectors that are exactly the same distance away from him, and the light starts where he is, right? So it spreads out and hits both of them at exactly the same time. They are simultaneous. But he looks at Henry's detectors, and why does he see Henry's detectors fire at different times? Because Henry's moving, according to Albert.
He believes the light strikes Henry's detectors at 2 different times.
Straight up laws of physics. Nothing funky here.
Meanwhile, Henry sees the same thing in reverse.
In other words, Henry sees Albert's detectors fire at different times, but his own detectors fire simultaneously. These are both intelligent people. They know physics. They're not being duped. And they are measuring events happening in different orders, because they are moving relative to each other, and because the one thing that they agree on, the speed of light, is the same for all observers.
They agree on the speed of light, but they disagree on whether events happen simultaneously or at different times. This is not semantics, nor a petty debate.
Big words. What's semantics? Word choice. Okay, semantics is a word that means you can choose different words, right, to describe things, right? The elephant was big or the elephant was massive. Those are two different words, right? And semantics would be, what are the similarities and differences between the choices of those words to describe the elephant, right? So, this is not semantics. This has nothing to do with word choice. It has nothing to do with philosophy, okay? Nor is it a petty debate. What does the word petty mean? Like small, insignificant, or stupid. Okay? It's not a small debate. It's not an insignificant debate. It's not a stupid debate. It's an important thing to be arguing over. And the argument is going to lead us somewhere. In order to understand why two people using immutable laws of physics are coming up with different perceptions of the same events, something has to give.
It means that time, as well as distance, has to be affected by motion.
So what's the other shoe that has to drop? Distance. So let's talk about measuring lengths. This one's a whole lot easier than time. Whole lot easier than time. We start with the hard one, okay? And we make it a little bit easier for you, okay? So, how do you know that this stick is a meter long? Because it says so, right? We define length by just saying, this is a meter, right? Okay? Are there any events involved? No, right? A length is a length, and I say, well, I start here, and I end here, and I call it a meter. So the measurement of length is very straightforward, mostly because it's just definition. Anybody remember what the original measurement of the meter, the definition of the length of the meter was?
King's arm.
Well, that was a yard,
Okay.
the meter.
I think they tried to measure from like both poles.
So really close. It was the distance from the North Pole to the equator on a line through Paris, France, divided by 10 million. It was 1/10,000,000th the distance from the equator. 10 million, 100,000, I can't remember what the factor of 10 is. But that's how they originally came up with the meter. Okay? It is now defined, does anybody know how we define the meter?
The speed of light.
The inverse of the speed of light. The distance light travels in 1 over the speed of light. Is 1 over the speed, right? Seconds per meter. Okay. So we've nailed the meter down to the speed of light. The one thing that cannot change, regardless of how fast you're going. So, what does that mean about a meter stick that is in motion? It is not still a meter. Okay? In the relativity of space, we've done the relativity of time and we'll continue to do it. But in the relativity of space, time stretches out, it dilates, it slows down. Lengths contract. It's called time dilation and length contraction. The give and take that is necessary in order for the speed of light to remain the same for all observers, regardless of relative motion, is that time intervals increase, meaning time slows down, and measured lengths decrease and get smaller. The faster something is moving relative to the observer, the shorter it will appear to be in the direction of the velocity vector. So, if I take this meter stick and I throw it at 9/10 the speed of light across the front of this room, I won't demonstrate. My contract doesn't allow it. Right? I can only do it in games. But if I throw this at 9/10 the speed of light, what will all of you and I see? A shorter meter stick in the direction of the velocity of the meter stick. If I turn it this way and throw it, what happens? It gets thinner. It would stay 1 meter top to bottom vertically, it would just get thinner. The contraction only happens in the direction of the velocity. So, what does that mean that spaceships should look like if they're moving? We have the Earth and somebody standing on the Earth. If the spaceship at rest looks like that, then what should the spaceship that is moving look like? I didn't do that very good. It should have exactly the same height but it should be a lot thinner. So the contraction takes place in the direction of the velocity vector. It's not like three-dimensional, everything gets squished, right? Things get squished along the axis of travel. We divide by gamma. We take a proper length and divide by gamma. What's the proper length? It's the length of the thing when it's not moving. That's an easier definition, isn't it? The reason it's an easier definition is because time is hard to measure. The concept of measuring a time is not well understood by a majority of people. Physicists might argue about what time is, but we know how to measure it. Lengths, much more commonplace for people to think about. How do you know a meter's a meter? Because you were told a meter stick is a meter, right? And as long as it's not moving relative to you, you can be assured that that is 1 meter long. As soon as it's moving relative to you, its length is going to be shorter by a factor gamma. That's what that equation is trying to say. All right. I have given you 2 very wild claims. And up to this point, I've asked you to trust me that what I'm teaching you is correct and true and valid and measurable. And so now I want to prove it to you. I'm going to prove it to you in several different ways. The first way is a direct application of length contraction and time dilation involving a subatomic particle called a mu meson. So I'm going to play a video that describes the actual experiment that was conducted using mu mesons by two gentlemen, Smith and Frisch or something like that, way back in 1940 something, 50 something. This was even before I was born. What's a mu meson? Decent question. It's a subatomic particle that's created when cosmic rays interact with the upper atmosphere surrounding Earth. Cosmic ray will slam into an atmospheric particle, strip off some electrons and some other stuff, and the mu meson is a very briefly, it doesn't last very long. It decays. It's a very unstable form of matter, and it decays very, very quickly. And we'll get into the numbers here in a second. But let me play for you the actual experiment involving mu meson.
A quarter of a century ago, Dr. David Frisch of MIT
This was filmed in
and Dr.
1982.
James Smith of the University of Illinois
So quarter century
built
before
a
that.
classic experiment proving the reality of the relativistic time dilation. They did it by measuring the flux through the atmosphere of a radioactive subatomic particle called the mu meson,
Back before Excel, you had to draw your own graphs in chalk.
created at the top of the Earth's atmosphere by cosmic rays from outer space. Mu meson zooms straight downward at nearly the speed of light. But laboratory experiments, such as the one done here by Smith, show that mu mesons disintegrate naturally after an average life of only 2 millionths of a second. That means that even going at near the speed of light, they shouldn't make it very far through the atmosphere before decaying. Or to put it differently, when Frisch and Smith observed 568 mu mesons in their detector at the top of Mount Washington, they calculate that only 27 per hour ought to make it to the base of the mountain. But when they cart their equipment down to sea level, they find almost as many mu mesons as they had at the top, 412 per hour. Of course, Frisch and Smith really aren't a bit surprised. The reason for the discrepancy is spelled out by the theory of relativity. Traveling at nearly the speed of light, the mu meson's internal clock runs slow so that, as viewed from Earth, they take much longer on the average than 2 millionths of a second to disintegrate. Or, to put it differently, as viewed from the frame of reference of the mu meson, the Earth's atmosphere, rushing upward at nearly the speed of light, is Lorentz contracted to such a degree that the particle can easily make it all the way to the ground in only 2 millionths of a second.
All right, let's untangle this. Okay, so here's a mountain, okay, and here is a mu meson, okay. We'll ignore, I think I've got most of these. That distance is about the same. So they said in the film, right, that the mu meson lives this long. Its existence is very short, okay. So in the laboratory, generating a mu meson that's just sitting there, okay, it will take, on average, 2.2 times 10 to the minus 6 seconds to decay. In other words, it's created, and then 2.2 millionths of a second later, it's split apart into its constituent parts and is no longer a mu meson. So the speed at which, the speed at which these things form in the upper atmosphere when a cosmic ray produces one is 99.5% the speed of light. So they're really moving when they are generated naturally. Okay, so if Mount Washington has a height of 5 kilometers, pretty close. Okay, Mount Washington's in the state of was it New Hampshire? I think. It's not really in the I just want to go on record, okay? We have mountains here in the west. Right? They have hills. Anyway, 5 kilometers high, okay, from sea level. The gamma factor for this, 1 over the square root of 1 minus v squared over c squared, you put it in, you get about 10. It's kind of a handy, 99.5 is about 10. You round, it's like 10.01 or 2 or something like that, right? So, with a gamma factor of 10, right, and a time in the lab, 2.2 times 10 minus 6 seconds, we have to figure out why it is that almost as many mu mesons are making it from a detector when they detect at the top of the mountain versus a detector at the bottom of the mountain. Now, how far could a mu meson go if it exists for only 2.2 times 10 to the minus 6 seconds? How do we find out how far it could travel? We are not doing anything. This is not new physics. This is old physics. This is chapter 2 physics. How far does something go when it's moving at constant speed for a certain amount of time?
It's not square root of 2gh.
It's not square root of 2gh. Okay. We know the velocity, right? 0.995 c, right? And 2.2 times 10 to the minus 6 seconds. The answer here, what am I asking? Distance. Where's my distance? 656.7 meters. In other words, if a mu meson's created in the atmosphere, and they're created all throughout the atmosphere, but let's just say it's created at the top of Mount Washington, okay? 5 kilometers above sea level. It could travel 656.7 meters before it breaks apart. But Mount Washington is 5 kilometers tall. It would not make it to sea level. We should be detecting way more. No, we should be detecting close to 0 mu mesons at the base of Mount Washington compared to the top of Mount Washington. There's a 5 kilometer difference. But the experiment showed that there was almost just as many. There's a discrepancy of like 100 mu mesons. So how do we display that discrepancy? There's more atmosphere down low, right, than there is up high. And so there's more opportunity for mu mesons to interact with another particle of the atmosphere and break apart and not be measured. But still, it was like 412 compared to 500 and so it wasn't 0. So they're measuring a lot of more mu mesons than physics says, straight up classical physics says, could be existing down there. So how do we solve the discrepancy? We reach for relativity. Because from the point of view of the mu meson, what is this number? Is this a proper time or a dilated time? That's a proper time. This is known as the decay rate in the rest frame of the mu meson, meaning it's not moving. This is a proper time. But according to the mu meson, it's standing still in its frame of reference, and what is the rest of the universe doing? moving at 99.5% the speed of light, which means as the mu meson, right, from our point of view, comes in, it's created from that cosmic ray and is hurling towards the surface of planet Earth. The mu meson is going to see the surface of planet Earth coming at it at 99.5% the speed of light. That 5-kilometer length for the height of Mount Washington, proper or contracted length? It's proper. Do we measure mountains' heights when they are in motion compared to us? No. Here on Earth, we say, well, that distance is 5 kilometers. It's not moving. Unless you had a really good spring break. In case we got to talk. Okay? But that's a proper length, according to the Earth. But from the point of view of the mu meson, it sees that 5 kilometers in motion. So is the mu meson going to measure a proper length? It's going to measure a contracted length. And how contracted is it going to get? So the mu meson, which in its own frame of reference only exists for 2.2 times 10 to the minus 6 seconds, doesn't see a 5 kilometer distance, it sees a 500 meter distance. And it knows, well, I can go 656.7 before adios. So can it make it? Absolutely. And you should measure, outside of scattering potential and the thickness of the atmosphere getting bigger down there, you should be able to measure just as many mu mesons. The bottom of Mount Washington is the top. According to the mu meson, the Earth's atmosphere is Lorentz contracted, length contracted, enough that it can make the trip. Let's argue from a time dilation point of view. This is a proper time because the meson comes into existence and goes out of existence in our laboratory at exactly the same place. But as we observe mu mesons being created way up there and moving, we from planet Earth would not see 2.2 times 10 minus 6 seconds. We would see a dilated time, a creation and annihilation happening at two different locations. And so we go to measure what that dilated time is, and we get 22 times 10 to the minus 6 seconds. How much time, according to us, is required for a mu meson moving at 0.995 c to traverse a 5 kilometer distance? Well, again, that's straight up physics. It's distance divided by velocity. The distance, 5,000 meters. The velocity, 0.995 c. Which gets me a time of 16.8 times 10 to the minus 6 seconds. So, if according to us, the mu meson is in existence for 22 times 10 to the minus 6 seconds, but it only needs 16.8 times 10 to the minus 6 seconds to go that distance, is it going to make it? Yes. This experiment cannot be explained without reaching for relativity. The results of this experiment are not classically verifiable. And it's not the only one. What?
So theoretically, you could do this experiment on like different planets with different atmospheres and try to.
You can do it on planets with no atmospheres. You just got to be able to make mu mesons. It just so happens that mu mesons are things that happen, are created in our atmosphere and cosmic rays, and therefore we have a natural laboratory with which to conduct experiments.
Right.
So, In 1971, J.C. Haefel and R.E. Keating took two atomic clocks and synchronized them. Now, atomic clocks, so you know, are hyper-accurate clocks. They only lose 1 second of time over stretches of about like 100 million years or so. What was going on 100 million years ago on this planet? Dinosaurs were, okay, doing their thing, right? So if we had an atomic clock that started back then today it would only be off by 1 second. Your computer is off by 1 second like every 4 hours. Okay? How does your computer or your phone or anything else keep time nowadays? The internet. Because there are time signals built into the internet, required by the TCP/IP protocol for sending packets places, okay, and reassembling packets in the correct order, that are governed by atomic clocks. And so every device that connects to the internet can read that time signal and resynchronize itself. Your computer and your phone do it all the time because silicon is a horrible timekeeper. So, atomic clocks, hyper accurate. They synchronize these clocks down to the femtosecond or something like that because that's the resolution of the clocks. They left one at their office in Virginia at the National Institutes of Standard Technology. They put the other one on an airplane and flew it for 45 hours. They refueled it. When they brought the clocks back to each other, they were out of sync. Why? Forgot to plug one in.
Because when the clock was moving in the atmosphere.
Because one was moving and the other wasn't. And the one that was in motion had slowed down, had not counted the same time interval as the other clock that had stayed home in the way. Now this, I will give you, is not special relativity. Why? By definition, we have to accelerate one of the clocks, right? So Haefel and Keating, being physicists, did general relativity calculations, the ones that allow for acceleration. And as you'll figure out, the mass of the Earth and all of those kinds of things, right? And their calculations agreed with the observed time discrepancy. But wait, there's more. Before we get to more proof, let me show you some simulations. Now, we can't move you to the speed of light. We'll talk about, when we get to general relativity, we'll talk about why. Okay? What we can do is cheat. And by cheat, I mean use CGI. Okay? Whereas most CGI in Hollywood is not based on real physics, it's based on movie physics. Anybody that's ever played in Blender or any of these other things, okay? The physics engine there is widely programmable to do whatever it is you want it to do, okay? What I'm about to show you are supercomputer simulations of what it would look like to be moving at high speed. So in this particular clip, we're going to show you approaching the Eiffel Tower. Paris is always in here somehow, okay? Approaching the Eiffel Tower at half the speed of light, and then we're going to go 90% the speed of light, and then we're going to go 99% the speed of light. Now again, we have to cheat here with time. Think of this as like the world's best slow motion camera, okay? We have to really kind of extend our time axis here, because if we had you fly towards the Eiffel Tower at half the speed of light, you wouldn't be able to see it, right? Okay? So we're messing with time here a lot for the simulation. But everything else besides the time interval is hyper accurate to what you would observe based on your constant speed of approach. And doesn't look out of the ordinary, does it? Why not? What's gamma for half the speed of light? Do you remember? It's like 1 still. It's like 1.001 or something. Like it's stupidly small. Like, remember, you have to be moving really fast to be able to see the effects of special relativity. So that was a baseline. That was a calibration. That was showing you kind of what it would look like normally. So here is 9/10, so 90% the speed of light. Doesn't look very different until, what? Wow, okay. What happened? Got distorted, didn't it? So, you're approaching the Eiffel Tower, but the Eiffel Tower has height and width and all kinds of dimension. And points farther away from you will appear to be moving slower than points that are close to you. You ever driven on the freeway and the cars way down there don't seem to be doing very much until they get next to you, right? Okay. Relative motion, relative velocity can remain constant, but perceived velocity of objects can change based on how far away those objects are and what directions they're going. So different parts of the Eiffel Tower are moving at different speeds. Even though you're approaching the Eiffel Tower at a constant speed, what you're seeing, right? And you saw some of the distortion, but 90% speed of light, gamma factor is only like, 2 or something like that? It's not very big. So here's 99% the speed of light. There's the top. Okay. We haven't gone through yet, but now we get to see the backside of the rear leg and then the top of the Eiffel Tower before we've even passed through the entire Eiffel Tower. Did you intuit that that's what it would look like? No. No, there's no intuiting this. Okay? We don't move this fast, right? On normal. Okay, so let's go Star Trek. Here's what it would look like flying past Saturn at 99% the speed of light. We've now passed Saturn, but we can still see it. I don't make up the rules. I teach them. And I like to think that I teach you truth. I lie a lot for your sakes, but I'm not lying now. Here's again another little cheat. I want you to watch the movement, okay? I'm going to read off the speed of light for you. So they're going to change the speed of light on you here. So again, this is a bit of a cheat because it's not special relativity, it's more general relativity. But the idea is the same. So we're going to start at 0, we're going to get up to 99, and then we're going to come back down. So 0, 20, 30, 40, 50% the speed of light. 60, 70, 80, 85, 90, 95%, 96, 98, 99, and coming back down to 50, 21, 0. Let's watch it again. Coming up, 30, 40, 50, things look a little distorted, right? 60, more distortion. 70, starting to see the tops. 80%. We're going to go up to 90, and we're going to be able to see the other streets. At 99, the other streets begin wrapping over the top, and we can see a street over. How did Albert Einstein do this without a supercomputer? Right? It's crazy. And yet, it's true. How many of you have ever used your phone to get somewhere? Everybody does it, right? Nobody uses maps anymore. You just ask Google or Siri or whoever, right, to take you someplace. Cars have it built in now, right? GPS navigation. So how does GPS work? Satellites. It's a correct answer, but it's a dumb one. Okay? Because people stop thinking after that. Why are the satellites important? What are the satellites giving you? A signal, a location, but can you determine the location from only one point of reference? No. In a two-dimensional plane, you need two pieces of information to determine where you are, right? An X and a Y. Okay? But what happens in a three-dimensional situation? Yeah, you have to have three pieces of information. Actually, it's a lot more complicated than that. To find your place on a two-dimensional surface, you actually need 3 points of reference. You need where you think, if you don't know where you are and you have a map, you need to be able to know where, say, one mountain is and another mountain is, and then you have to draw an intersection, okay, based on bearings to those two mountains. When you go to 3 dimensions, you actually need 4 pieces of information. Because you have X and Y on the surface, and you've got the curvature, and so you need distance from center of planet. That requires, you can get away with 3, but if you want elevation information, you need 4 distinct measurements of how far away you are from something else. And with GPS, the distances that your receiver is measuring is the distance to a GPS satellite. 4 of them. Minimum 4, preferably more, because the more satellites you have, the more data you have, and the more exact your location will be. Have you ever looked on your phone and watched it initially say you're here, and then somewhere inside this bubble, and then after a little bit the bubble shrinks? What's going on? It's doing more math and getting your location more precisely. Now, you should know that most cell phones cheat like crazy. They do have GPS receivers in them, and you can get your location to within about 1.5 meters of where you are on GPS alone. But if you're in a city, you can get even more hyper-accurate information based on Wi-Fi and Bluetooth. So what happens in our cell phones is actually called assisted GPS, where they use known distance from Wi-Fi antenna and Bluetooth devices in order to triangulate. Okay? If you have an Apple product and you've ever played around with an AirTag, okay? If you have Android and you've used a tile, okay? Those are things that give off low frequency radio signals that any device can pick up and anonymously send to the internet so that you can know where devices evolve. Anyway, GPS in your phone works by knowing how far away a minimum of 4 satellites. Now, the GPS constellation is designed so that there will always be 10 satellites above the horizon, no matter where you are on planet Earth. They just put them in the right orbits to guarantee out of the 29 that are in the system, 10 of them will always be above the horizon. So, minimum 4. And what sort of information do you need to know how far away that satellite is? Well, you need its position, but how are you going to determine where it is? It doesn't know where it is. It's in orbit around the planet, right? So it's the one thing that satellite can send to your phone. Hint, it's not a letter. A signal, a radio pulse. Traveling at what speed? Speed of light. And the speed of light is the same for all observers, regardless of relative motion. So that satellite, which has an atomic clock on it, can send a radio pulse to your phone, telling your phone what time it was when it sent the pulse. If you know what time it was then, And you know what time it is now, because your phone can ask the internet what's the standard atomic time, right? And you know that, so now you have a time difference, and you know how fast something, what can you now calculate? Distance. What's the problem? Something is moving. What's moving? Both things. You and the satellite. You're rotating on the surface of the planet, and the satellite's in its orbit. You have to make a relativistic correction for the motion of the satellite and the difference in distance between the center of the Earth for both you and the satellite in order for GPS to be accurate enough to assist in navigation. If you just take the time signals from the GPS satellite and you don't do the relativistic corrections, then at best you can know your position to within plus or minus like 1.6 kilometers. Which is nifty, but not useful. Take it from a former search and rescue person who was trained in wilderness rescue. In other words, people who get lost in the woods. Okay? If we know where somebody is to within a kilometer, they might as well still be lost. It's still going to take us time, depending on how many resources we have, to find them. But if we know where they are to within a meter, they're found. Right? Because it only takes one person to go to that spot and see where they are, as opposed to hundreds. It's a big difference. It only works because of relativity. This device that my kids don't know how to use maps. I've tried so hard to teach them how to use real maps. When they need to go somewhere, they just pull out their phones. How do I get to school? I was like, open your eyes. You go down the same road every day. We live in a world where we have to know about relativity in order to get these things to work. So, mu mesons, Hefel and Keating flying atomic clocks around, GPS, all of these things require relativity. Your phone does relativity every day, all the time. Figure out where it is. A satellite was launched now about 20 years ago for the sole purpose of determining whether or not Einstein's general theory of relativity was holding within the vicinity of planet Earth. It was measuring something called the frame drag. I'm not going to get into what that is. But the spoiler version of the entire story, and it's a good story, it's got some twists and turns in it, but the spoiler version is that they measured the general relativistic effects of the Earth's mass on that satellite to within 1/10 billionth of a percent error. We can't do that with Newton's laws. Like, at best, I can do 1/1000th of a percent error with that. Okay? We have shown over and over again. I'm going to give you more when we get into general relativity. We're going to talk about how they knew general relativity was true and why Albert Einstein went from being nobody to everybody overnight. Okay? We'll talk about all of that. We'll prove the experiments that they did in 1920, right? 1919, actually, to show all of that. But you need to know this. It's very important. I feel like Han Solo in The Force Awakens. It's all true. Everything that you've heard about relativity, the actual physics of it, not the science fiction stuff like that, right? real. It is not a figment of our imagination. And we will continue to explore the strange reality of it on Wednesday. What's happening tomorrow? Test autopsy.